I think you remember that we discussed in last class about yes, momentum based gradient descent method, right? So what is momentum based gradient descent method? It is an improved version of gradient descent method because gradient descent methods fail when your functions are flat. Okay, we took one example where in x direction it was elongated, so it was flat along x direction and it was short in terms of y direction. Okay, so this motivated us to consider some momentum, like how to add momentum to it so that like it can be faster. We can achieve the moment, like the optimization faster. Now there is another algorithm which we won't compare with momentum, but it is somehow better. Okay, so it is another class of another method which is known as RMSProp, known as root mean square propagation. Okay, so that is RMSProp method. It is also an optimization technique, but most importantly, it is also used in deep learning. Okay, gradient descent might not be used in deep learning, but variants of the gradient descent method is useful in deep learning. Okay, please note this statement. Gradient descent methods might not be directly used in deep learning, but variants of gradient descent method is used in deep learning. What are the variants of gradient descent method? Stochastic gradient descent, mini batch stochastic gradient descent, Adam optimizer. Okay, we'll cover this in this within 1 hour, and we won't go too much of detail. Like we'll just tell you what is. You'll get a feel of what is Adam optimizer and how it works. That much. We'll not see much into the computational aspects of Adam optimizer. That I will leave it to your deep learning class. Fine. So RMSprop is coming from algorithm. Now it's not clear why we have used the word root mean square, but soon it will be clear as we move on. So it's an adaptive learning rate optimization algorithm. So how to adjust the learning rate adaptively. Okay, we saw that if we fix a learning rate very like constant throughout the optimization process, it is not that efficient. So we saw at one point that if you decrease the optimization learning rate, it is good. When you increase the learning rate, sometimes it is good. So then researchers thought that how about adjusting it dynamically? Like with number of iterations, learning rate should also change. Okay. So therefore, in momentum based gradient descent method, we came to know about the concept of leaky averages, that is a moving average. Okay, so same concept is used in both RMSprop and also in Adam optimizer. Okay. So it uses leaky average, but rather than I urge you to look into your notes or whatever, like in momentum based gradient descent method. In momentum based gradient descent method, you were using the past value of gradient, but here it is a bit different. Instead of past value of the gradient, you are using the past value of the squared gradient square. Okay, that's the only difference. Fine. So we are using the squared gradients, and we will take all. And what is moving average? Moving average is nothing but giving more importance to the current weight, okay, current value, and also giving very less weight to the past values. Okay, that's is known as moving average. You give more weightage current value and less weightage to the past values, past sequence of values. That's exactly we are doing here. But instead of the past values, we are taking the past value squared. Okay, gradient squared. So you will see summation of gradient squares. Okay. And instead of summing them indefinitely. So you will see that usually what happens here is learning rates shrink very much. And if learning rates shrink very much, you already know that if learning rates shrink, what happens? If learning rate shrinks, what happens? It will, yes, it will take more time to reach to the optimum, or maybe even doesn't reach to the optimum. Okay, but it might reach to somewhere which is not an optimum. We saw that. We saw that. Okay. So in that case, RMS prop is helpful because if you take the square of the past gradient, this doesn't happen. So here the gradient magnitude matters. Okay, so why squaring the gradient? So you can see the squaring the gradient captures its magnitude, which ignores the direction. Okay, large gradients contribute more, while small gradients contribute less. So if you square this, what will happen? If you have a small value of gradient, if you square it, it becomes more smaller. If you have a large gradient, if you square it, it becomes much larger. So thinking about that, it has been designed. And last class, I just surfaced through this slide. Okay. So you can see, you can just check your momentum based gradient descent method. You can see that here in place of GT square, GT was used. In place of GT squared, GT was used, isn't it? You agree with me, right? In momentum based gradient descent method, in place of GT squared, GT was used. Okay. So this is, so we should use a squared gradient estimate here. Okay. So you can see ST is a variable and ST stores an exponentially weighted moving average of past squared gradients. Okay. I hope you can understand through this recursive relation that why this is like a exponentially weighted moving average, because the more and more iterative process you take it, you will get a sum, you will get a summation of those things. GP, geometric progression kind of thing, you will get here. Okay. What is gamma? Gamma is nothing but a decay factor. There we used, I think, beta or something, isn't it? So decay factor controls how much past gradients should influence your current estimate. I told you our aim is to give low control to the past gradients and give higher control to the current gradient, to the current value. So you can see gamma typically 0.9, that means st minus 1 plus 0.1 gt squared. Okay, so you can observe from this the coefficients. Fine. Okay, so this is how you update, this is how you update your st value. And this is nothing but a variant of gradient descent. You grad of f at that x, isn't it? Yes, that is the simplest version of gradient descent. And whatever we have been doing in the past 3 weeks, we have just now we have done nothing. We have just modified this to get stochastic gradient descent, to get mini batch stochastic gradient, get momentum, get root mean square propagation, and also you'll see to get Adam optimals. So therefore, gradient descent is well famous. Even though the raw version of gradient descent won't be used or might not be used due to its lack of efficiency in some cases, but variants of gradient descent method is used, and therefore gradient descent method will always come to picture, and that's why it's so famous. Okay. Fine. So this is the idea. So you can see here that xt is equals to xt minus 1, same as gradient descent, minus eta times this is the learning rate, okay, times divided by root of st plus epsilon. Okay, root of st. What is st? St captures the information of the squared gradients, isn't it? And you are taking a root over that. You are taking a root over that. Okay, so therefore, I hope you can understand why it is root mean square. Okay, you got it. Why we are calling root mean square here. So ST captures the squared value of gradients and then you are taking a root over. This you usually see in root mean square speed in physics in many applications. Root mean square speed when you are studying about kinematics or many other things. So from that you can see why it is obvious that it is called as root mean square propagation. So where this epsilon came from? So it can be that st equals to 0. It can be. Okay, it should come to your mind that gradient is nothing but a variant of a slope. Okay, gradient is nothing but a variance of a slope. Okay, so slope can be 0, so gradient can also be 0. So to prevent that scenario, if gradient equal to 0 and epsilon was not there, then you're dividing by 0, right? So to nullify that effect, they add this bias term, that is small epsilon, okay, which can be typically small, that you can see 10 to the minus 6. Okay, anyway, and this symbol you are seeing is the element wise multiplication, just like dot product. Okay, fine. So here in orange, I have written here why it is called as root multiplication, because it takes the square root of a moving average of square gradients. You are taking a of moving average of what? Of square gradients. That is, you saw why it is square gradients. Okay, you saw, because you are taking nothing but here gt square. Fine. Therefore, it is known as root mean square propagation. Fine. Anyway, so yeah, why we took epsilon greater than 0? It's typically set to 10 to the minus 6 to ensure that we don't suffer division by 0. Okay. Else it will just diverge. Else your optimization algorithm will just diverge. Like you are here and it is doing like it is trying to reach this optimum, but the moment if somehow gradient turns out to be 0, then it will just spike up. It will go towards infinity if you are dividing by 0. So therefore there is plus epsilon term in the denominator. So you can see this is nothing new to you. This is nothing new to you. Like, yeah, you can apply the same reasoning. You can apply the same reasoning as before, as applied for the momentum case, and iteratively apply it. Okay, write t in terms of t minus 1, write t minus 1 in terms of t minus 2, t minus 2 in terms of t minus 3, and you are developing this infinite series. You are developing this infinite series same as in the case of momentum. But instead, what you see the difference as compared to momentum here? Yes, it's just gt squared. Otherwise, it should have been in momentum, it is just gt. Okay, but yeah. So you can just apply this GP identity, geometric progression identity. Okay, and yes, you can get it. I think we should see this in Python maybe. Let's see. Okay, anyway, we'll just cover this why it is being used. So you can see the main reason why we are using RMSProp is if your learning rate keeps on diminishing or continuously decreasing, then here through this method you adaptively change your learning rate respect to iterations. Okay, fine. And how you do this? By taking the moving average of square gradients. Okay, this is the knowledge you might not be able to recollect in your mind or connect these two. How suddenly learning rate problem is fixed just by taking the square of gradient summations. Okay, but this is just the idea I'm giving to you. If I go deep, yeah, like we could go deep, but I don't want to focus much on this. Okay, but I am giving you just an idea like where the up-to-date current optimization methods are in deep learning today. Right. So because if you see today I was seeing like I am planning to cover regression today. So after the break we will start with regression. But the idea is like during regression you will see in Python, I don't know if it is already covered in some of your class, curve fit in Python. Okay, you just give your arguments x and y and it will just do you don't need to worry about formulas and anything. Okay, so but how curve fit works in Python? Okay, what is inside curve fit? Inside curve fit, it is using an optimization algorithm which you did not cover in class. So but then I feel it a bit offended because I don't usually cover it in like like my aim is to cover optimization techniques which are actually implemented inside Python. But I got sad by seeing that algorithm. It's an optimization algorithm for profit, but I am not teaching that in class. So I want to teach optimization algorithms which are used inside Python. Okay. So of course, then it won't be available in textbooks. It won't be available in textbooks. Okay. Because you can see even in numerical methods textbook, you borrow from library, whatever is teaching here, like gradient descent and all, you won't find in numerical methods books. And that's a bit unfortunate because the books should evolve according to the year with the current topics. And of course, one needs patience, one needs effort to write books, but you should not waste your semester because a book was not written, isn't it? So therefore, it is a job of a teacher to understand the real scenario and come to here to teach. Okay, and that's what I try to do it here till Adam Optimizer, maybe just 0.01 addition to what in the last semester, but gives me some kind of happiness that somehow something is covered. Okay. So what will you do if you encounter non-convex optimization problems? So after maybe after one semester or something, some students can tell you how they have converted some non-convex optimization problems to convex optimization problems. Okay. So there are different kinds of optimization algorithms. So you'll see it. So similar to momentum methods, yeah, similar. It is very similar to momentum. The one difference, squared gradients. Just one difference. And some more things about RMSProp. It stabilizes your training. Okay. It stabilizes your training by reducing the learning rate when gradients are large. Remember this carefully. It's a very important statement. So by how it stabilizes the training, just read this. Reducing the learning rate when gradients are large. You know that you are multiplying the learning rate with the gradient. Okay. And this is your time. This is your step. This is your step. Okay. So you don't want this to rapidly change. You don't want this to rapidly change, but rather change it smoothly. So if eta increases, how you can reduce its effort? Decrease the gradient. You got the idea. If eta is increasing, you reduce the gradient. And if eta is decreasing, you increase the gradient. And that's exactly, this idea is exactly being taken care by RMSProp. Okay. So this should ignite some of like your inner things that I want to go deep into RMSProp and understand how this is being taken care of. Okay, so I have told you many important points of RMSProp, but I understand that you are finding a bit tricky to like coordinate each of these points, but that's for your suspense, how you take it up. Okay, so yeah. So before we begin this, we'll just see one Python code just to show you. Let me see if I have that Python code with me. So So I discussed this last class, right? Yes. So you can see this RMSProp algorithm. Okay. So we have these two optimization functions like 0.2. Sorry, no. What is my optimization like cost function? Huh. Yeah, it is the same function we had taken last class. 0.1, you can see from here. This was not working with gradient descent. Remember that in the last class when we were covering momentum based gradient descent, we told why we started with momentum based gradient descent? Because gradient descent was not able to minimize this function, okay, this objective function. Okay, therefore, we came to momentum-based gradient descent method, and now what we are doing, we are applying the same objective function using RMSProp algorithm so as to optimize this function. So what we are doing here, we have taken, you can see, I think, yeah, two different gradients like G1 and G2. Why two different gradients here? Anyone? Are these two different gradients? What are these G1, G2? What is G1 and G2? You tell. What is G1 and G2? Yes. First is with respect to x1, second is with respect to x2. Yes. And epsilon we are fixing 10 to the minus 6. And same thing what you saw in your slides, we are just doing it. S1 and S2 to capture the values. What is S1 and S2? S vector. S vector is just nothing but S1 is the first component, S2 is the second component. Okay, S1 is gamma times S1 plus 1 minus gamma times the squared of the gradient. Is this exactly what you have seen in the slide? S squared of the gradients. And same we are doing with S2. And after that, you can see like the root mean square propagation algorithm we are applying. X1 equals to X1 minus. X1 equals to X1 minus eta, the learning rate, divided by square root of S1 plus epsilon. I think I did one mistake there in the slide. I'll come to that. Times G1. Times G1. Yes, yeah, you remind me when I come back to the slide. You remind me about the square root. Okay, I'll tell you. So then just return x1, x2, s1, s2. Okay. And here we are training it by iterating it for number of steps. I think for 20 or 30 steps. Okay. You can see like this, and we are appending it in the trace. Okay. And then we will plot the trace. After appending all the values where x1, x2, here x1, x2 is in the first iteration. Next iteration, you do the x1, x2, store it, the values. Okay, then what you do while plotting, you have 2 points. Can you plot those using a straight line? If you have 2 points in Python, just plot it by a straight line. So therefore, you are seeing these zigzag things in the output, in the plot. Okay, that's exactly the plotting. Okay, we are plotting, we are appending all in trace. Okay, you can see np dot array trace. It has all the data of the iterates how it is moving on the phase space, like on the space. Okay, where your optimization function is, where your cost function is. And here then we are plotting it. Here we are plotting it. Okay, so you can see when we are doing it. So my starting initial condition was here. Okay, you can see these are the ellipse you plotted in the last class. You remember this function, I think. Okay, it was stretched on the x-axis, it is flatter on the x-axis, and due to this gradient descent method failed. Okay, fine. So therefore, it is just an example to you that you won't get in real life, that it is 0.1 x1 square plus 0.2 x2 square like this. But the moment you see in your data set, or whenever when you're trying to optimize anything, you see something flatter, you see anything like a flat function, then suddenly it should come to your mind, no, I should not use gradient descent, I should use either momentum or RMSProp or Adam. Okay, now you know that Adam optimizer is the most efficient one, so use that. But at least to know that Adam optimizer to use, at least you know the path how Adam optimizer was taken into consideration. Okay, so you can see how nicely it has converged to the optimum. Smooth. It is very smooth. Started from here, then I don't know how it knew it came here, then okay. So I suggest you try gradient descent optimization algorithm for this function. I did not show you. in Python and check whether the function is not. We saw that, right? We saw gradient descent using this, right? We saw that gradient descent, it took, I think, lot of iteration steps. I think 45 iteration steps to just converge to this. Yes. Okay. Okay. So now you know that yes. Change in. Yeah, yeah. So there was a tiny mistake here. So instead of the square root covering only st, you remember that epsilon is 10 to the minus 6. It should come to your mind suddenly that if epsilon is 10 to the minus 6 and it is st is 0, then you are dividing by 10 to the minus 6. What is actually it is doing if you are dividing by 10 to the minus 6, it is actually multiplying it by 10 to the power 6. That is a very high quantity, right? So then you can say that, sir, it can diverge. 10 to the 6 you are multiplying. But I did not see that observation from your side. Okay. So therefore, when I saw the Python code, I just remembered that, yes, I forgot this square root. So instead of this, it should be you're taking the square root of st plus epsilon, not only square root of st. Okay. That's the catch. Because if st equal to 0, you are dividing by 10 to the minus 6, which is equal to 10 to the power 6. And therefore, you are multiplying 10 to the power 6 to this guy, which is very high. So this is just the change here. This you will see in Adam Optimizer also. No, in Adam Optimizer, it will be a different one. You will see. What's the difference between the square root? Okay. So, fine. Okay. So we'll just cover the theory for Adam Optimizer. We won't detail. I will leave this to your deep learning class to explore. But at least you now know how Adam Optimizer came to picture. Okay. So you can see Adam, it was founded in 2014. Ingma and Ba, you know, in 2014 combined all these techniques means momentum based gradient descent plus RMSProp, okay, algorithm into one efficient learning algorithm, okay, and that's what is you will see like suddenly if I did not teach you all of the things and suddenly I teach you this, that how you are missing out a big part, okay. So you can see now Adam Optimizer is not independent. It has borrowed the uh, left hand from momentum method, right hand from RMSProp, and what is the middle part? Middle part is gradient descent. Okay, that's how Adam Optimizer. Okay, Adam. Adam is like the Superman. Adam was there, right? Adam. I heard after Superman, Adam came, right? Black Adam, huh? Black Rock is it? There is Adam and Eve also. Okay, but yeah, recent movie, right? So as expected, this is an algorithm that has become rather popular as one of the most robust and efficient uh, optimization algorithms to use in deep learning. Okay, so therefore, I hope in your deep learning class now, in every class, without the term Adam, your class might not proceed ahead. Okay, they might be telling you Adam multiple times in the class. How many of you are taking deep learning? All. It's compulsory for all, but most are taking. So you can see that at least there are some algorithms which are useful in deep learning. Okay. So, but anyway, it is not without any issues. Adam optimizer also has issues. Okay. In particular, you can see Reddy et al. Has shown in 2019 that there are situations where Adam optimizer can diverge due to poor variance control. Okay, variance control means variance in the gradient. Okay, variance in the gradients. We saw in the last class. Okay, we saw in the last class how mini batch stochastic gradient descent was able to minimize the variance of the gradient. We showed that whatever gradient expectation we took, we showed the original gradient. Okay, because you are taking the samples from the data set itself independently. Okay, so you can see a hot fix to fix this Adam optimizer in those failing cases. Another algorithm came up known as Yogi. Okay, it's known as Yogi, but I will not cover this. If possible, I will just make a class by myself and share it with you. So Yogi, it's nothing far different, but just a minor adjustment to Adam optimizer. So to address these issues, like you can see, and what Adam optimizer does, Adam optimizer takes care. This is the most important part in red. Most important part. It will take care of exponential moving averages again. Okay, what you have seen so far in momentum and RMSProp. But here for two cases. Here for momentum as well as variance. Okay, two cases. We'll see. Adam uses exponential weighted moving average to estimate two cases. First case, the momentum Vt. Remember these notations. If I am, so you know, in momentum gradient descent method, I used Vt. What we did in momentum based gradient descent method, instead of taking the gradient, what we took? We took the momentum, that is Vt. Okay, that was the catch. That was the main part of the momentum gradient descent. So here also we are doing the same. So we are taking the exponential weighted moving average to estimate the momentum Vt at particular time step t or at an iteration t. I should have written n, but I'm showing you that with respect to time it is moving. So you can see it is a running average of gradients, of course. And second, this is the most important one, is the second moment. I told you. Did you guys read the moment or anything in statistics? I told you are seeing it, moment generating functions and all those things. Where moment is coming. In moments, I think you know where the summation comes. Okay, and here also in momentum based gradient descent, in like RMSProp and all, summation is coming. So there is some relation between it. I wanted you guys to revisit that so as to you can understand the correlation between statistics and this case. Moment is coming, first moment, second moment, third moment, nth moment in statistics to here. Okay. Here, second moment ST. Okay. So you will see in Adam optimizer, you will see two quantities, that is Vt and St. What is Vt? Momentum. What is St? Second moment. Okay. Second moment St you saw in RMSProp. St you saw in RMSProp, isn't it? St equal to St minus 1 minus something. Okay, that square root. A running average of squared gradient. So you can see this is momentum. This should you should remember about momentum when you to take Vt. Okay, and when you take running average of squared gradients, it should remind you of yes, RMS. So now you can see how Adam optimizer is built from RMSProp and momentum method. Okay, so therefore it was necessary for me to cover RMSProp and momentum. Okay, so in order to cover momentum, I have to cover gradient descent, and also if I am covering gradient descent and RMSProp, I have to cover mini batch and stochastic. Okay, so therefore everyone was interrelated. So without telling this main story, I had to cover all this. So you can see we are updating the moving averages for momentum and variance, same as before. This is for momentum. You can see we are just taking the gradient GT. We are not squaring it because it's a part of momentum. Okay. Same beta 1 1 minus beta 1. Vt is the, you know this is just the recapitulation of the momentum method. Okay, beta 1 is typically said this, it controls how much previous momentum we retain. Okay, fine. So this is all about momentum method, and this is all about RMSProp method. Okay, ST is going to beta 2 ST minus 1 plus GT square. So I hope you can see the difference between the two in blue and red. In blue we are taking G, ST we are estimating in this. So now the question is, now okay, using momentum based method we got VT, using RMSProp method we got ST. Now how Adam optimizer is making use of this VT and ST? Okay, that's the question. Right. So that's the idea. You can see we are doing some bias correction here. That is the next step. Since momentum and variance usually start with zero onwards, it starts with 0 onwards, it is more likely that when you keep on iterating, the values keep on close to 0. Okay, since you are starting from 0, if you keep on iterating, it is likely that your values will be close. To avoid it, we are adding some bias. Okay, that you will also hear the term bias much in deep learning also. Okay, we are adding bias. Okay. So they are biased. You can see since momentum and variance start from 0, they are biased towards smaller values. To fix this, a correction is applied. What kind of correction you can see here? VT cap is the correction, that is you are taking the VT which you obtained before, dividing it by the scaling factor it had. You just, I am taking it, you taking again, you can see beta 1 is multiplied with VT minus 1. Okay, so same beta 1 we are taking here, and similarly for the second moment. Okay, new second moment after adding bias, beta 2. Fine. Don't worry about much of this, just try to understand what is happening here, like just how Adam optimizer is working, what it is using. So then we are doing a gradient rescaling just like RMSProp, because if ST equal to 0, then it can shoot. And here it is different. How it is different? Instead of taking the full square root, previously RMSProp, we had taken ST plus epsilon. But in Adam, we are taking just square root of ST. We are just taking square root of ST plus epsilon. Why? Why this is the case is left to you. Okay, try to see why it is the case. Okay. So I am showing you the path, and somehow the bridge is not connected. It is your duty now to connect the bridge. So you can see, unlike RMSProp, Adam updates the momentum rather than using the raw gradient directly. Okay, so here also instead of using VT, you are using some combination of VT and ST through this, and that is our gradient for Adam optimizer. Okay, you can see VT we know, ST we knew. Okay, now I asked you the question, how are we using VT and ST? Okay, this is how we are using it, motivated by RMSProp. Might be complicated, but you can see where the square root is coming. It should just look like RMSProp algorithm. Okay, it should look like just like that. And after that, yes, it's usual gradient descent. Okay, it's usual gradient descent step. Xt is going to xt minus 1 minus gt prime. Why are we not multiplying the learning rate here? Already multiplied here. Okay, already multiplied eta there. So therefore, just use this updated gradient. So you can see how Adam optimizer how Adam optimizer is a, you can see that how Adam optimizer is a version of a gradient descent. Okay, you can see xt is xt minus prime. So Adam optimizer is also an iterative algorithm. Okay, and an iterative algorithm falls in numerical methods. Okay, that's the idea. Okay. So I hope you understood some part, like what is Adam optimizer? Adam optimizer is more robust because, yes, it is using both cases, like momentum based gradient descent and RMSProp. Okay, you can see that it uses both the momentum and the second moment to function properly. Okay, but it is finally, you can see it is a variant of gradient descent. Okay, how it is a variant of gradient descent. So yeah, so far this is the most efficient one because you are capitalizing all the previous method into this. Okay, that's how it is. I hope you can see, like past 10 years or past 20 years, the laptop you were using and now the laptop you are using. Now the laptop you are using is much faster, much better, coming with Windows 11 and all these things. But 20 years before, the laptops were not like that. Okay, so therefore, how they improved? They noticed what are the demerits in the past. They tried to improve it by using the current technology, and you are using the better one. Same works with Adam. So far, scientists have developed all these optimization algorithms. What Adam did, Adam took into the issues what others are facing, and the best optimization method is just combined, and that's how it is working. Okay, there is something known as Yogi, which takes care of Adam optimizer, the demerits of Adam optimizer. There is also something known as I wanted to cover, but I will cover like by myself and share it with you. Okay, it is just up to you to see or not. Like, but it won't come in any exam. Okay, but till now it can. So there is something known as learning rate scheduling. Okay, so this I wanted to cover, but I think we have to spend another class or something for this. But I don't want to go more because I covered till Adam optimizer, so that you know the we finished. We started with some low optimization techniques, and we went to the best. That's the route we took for this optimization in this module. So one of the module is completed. After the break, start with the new module, that is regression, and it will be very easy. It's nothing that hard, but you will see that the optimization method you learned so far, especially the Hessian and the Sylvester criterion, how it is being used in least square regression. Okay, we will see how that optimization is used in least square regression and how optimization comes in the place of regression in this class. Okay, so you can see just a summary. Adam optimizer combines momentum, just like stochastic gradient with momentum, and adaptive learning rates, that is using RMSProp. So you can see Adam optimizer. So if someone asks, does Adam optimizer uses adaptive learning rate? Yes. Why? Because adaptive learning rate module is coming from RMSProp, and RMSProp is being used inside Adam optimizer. So therefore, adaptive learning rate is being used by Adam optimizer. Okay, fine. So you can see the way we introduce this bias correction helps to update the helps you to helps ensure stable updates in reaching to optimum values. Okay. Anyway, it is widely used. You can see due to its fast convergence and robustness. So I hope you got some ideas behind this optimization module. Okay. So I think to this we will just add this. So last class I covered. I recapitulated. I went through all the methods we have learned so far in this course. Okay. So you can see we finished this one, Adam optimizer. So this slide has all the methods we have covered so far in the class. Of course, not in detail, but whatever. Okay. So I hope you got an idea. There are some parts I did not cover, like quasi-Newton method, but if time permits, I will create method on these three, like Yogi, learning rate scheduling, and quasi-Newton method, when time permits, and I can share with you. Okay. Fine. So through this, then you have a pack of optimization algorithms in your mind. So I suggest you don't need to. So after this module, I suggest you don't need to know tips and nicks of this optimization algorithm, whatever I have taught, but you should know the logic behind this. What is stochastic gradient descent? What is gradient descent? Why we went to gradient descent? Why, how multidimensional gradient descent method works? What is the disadvantage of multidimensional gradient descent? For that, how you can use stochastic gradient descent? Why we came to mini batch? Okay, then why we used momentum? Because gradient descent failed in some cases in flat functions. Okay, then why we started with RMSProp? Okay, why we started with RMSProp? So that it is just an adaptive learning rate method. Okay, how you can adjust learning rate. Usually, what happens in optimization algorithms, learning rate shrinks. Due to that, your optimization stalls. To avoid that, you have to use adaptive learning rate. That's exactly RMSProp does. Then we came to Adam Optimizer, which uses RMSProp, gradient descent, and momentum method. Okay, to make all those necessary changes. There are still some shortcomings of Adam Optimizer. Coming to Yogi method, it's, I will cover it separately. So that is the last, and then maybe you will see as I will share learning rate rescheduling, like how you can schedule these schedulers. Okay, that's that one. That one is the last. So yeah, that's so far the optimization module. I suggest to know like this, like a bit of theory here and there, how why it is working, why not it is working. Okay, you won't be asked details about this. Maybe I will give you the formula. I will give you the formula in the whatever test or wherever. Just to you need to know what they do. Okay, you need to know what they do. Okay, that's the idea. Okay, we'll take a short break, and then we'll begin. Okay.